A tyre is a ring-shaped vehicle component that covers the wheel's rim to protect it and enable better vehicle performance. Most tires, such as those for automobiles and bicycles, provide traction between the vehicle and the road while providing a flexible cushion that absorbs shock. The materials of modern pneumatic tires are synthetic rubber, natural rubber, fabric and wire, along with carbon black and other chemical compounds. They consist of a tread and a body. The tread provides traction while the body provides containment for a quantity of compressed air. Before rubber was developed, the first versions of tires were simply bands of metal fitted around wooden wheels to prevent wear and tear. Early rubber tires were solid. Today, the majority of tires are pneumatic inflatable structures, comprising a donut-shaped body of cords and wires encased in rubber and generally filled with compressed air to form an inflatable cushion. Pneumatic tires are used on many types of vehicles, including cars, bicycles, motorcycles, buses, trucks, heavy equipment, and aircraft. Metal tires are still used on locomotives and rail cars, and solid rubber tires are still used in various non-automotive applications, such as some casters, carts, lawnmowers, and wheelbarrows. Etymology and spelling. Historically, the spelling was tyre and is of French origin, which comes from the word tyre, to pull. The reason for this naming is that originally tyre referred to iron hoops or thick wires bound to carriage wheels. In French blacksmithing, the word for a drawn iron rod is a tyre, or pull. The same word was often used for any metal drawing or rolling process. In an article in the London magazine Intelligencer of 1853, The Utility of Broad Wheels, the author explains that the common practice was to bend two rods, called tyres, into hoops and bind them to the wheel. But it is preferable to use an iron band, called a broad wheel, rather than the rods, because as the rods wear, they bite into the wheel. Another early mention of a tyre in English is in the Scots magazine, volume 15 by James Boswell. Another etymology of tyre is provided by Online Etymology Dictionary, essentially that the word is a short form of a tyre, and that a wheel with a tyre is a dressed wheel. Some other etymologists may share this view. The spelling tyre does not appear until the 1840s, when the English began shrink-fitting railway car wheels with malleable iron. Nevertheless, traditional publishers continued using tyre. The Times newspaper in Britain was still using tyre as late as 1905. The spelling tyre began to be commonly used in the 19th century for pneumatic tyres in the UK. The 1911 edition of the Encyclopaedia Britannica states that spelling tyre is not now accepted by the best English authorities, and is unrecognized in the US, while Fowler's Modern English Usage of 1926 says that there is nothing to be said for tyre, which is etymologically wrong, as well as needlessly divergent from our own older and the present American usage. However, over the course of the 20th century, tyre became established as the standard British spelling. History. The earliest tyres were bands of leather, then iron, placed on wooden wheels, used on carts and wagons. The tyre would be heated in a forge fire, placed over the wheel and quenched, causing the metal to contract and fit tightly on the wheel. A skilled worker, known as a wheelwright, carried out this work. The outer ring served to tie the wheel segments together for use, providing also a wear-resistant surface to the perimeter of the wheel. The word tyre thus emerged as a variant spelling to refer to the metal bands used to tie wheels. The first patent for what appears to be a standard pneumatic tyre appeared in 1847, lodged by the Scottish inventor Robert William Thomson. However, this never went into production. The first practical pneumatic tyre was made in 1888 on May Street, Belfast by Scots-born John Boyd Dunlop, owner of one of Ireland's most prosperous veterinary practices. It was an effort to prevent the headaches of his 10-year-old son Johnny, while riding his tricycle on rough pavements. His doctor, later Sir John Fagan, had prescribed cycling as an exercise for the boy, and was a regular visitor. Fagan participated in designing the first pneumatic tyres. In Dunlop's tyre patent specification dated the 31st of October 1888, his interest is only in its use in cycles and light vehicles. In September 1890, he was made aware of an earlier development, but the company kept the information to itself. In 1892, Dunlop's patent was declared invalid because of prior art by a forgotten fellow Scot Robert William Thomson of London. Although Dunlop is credited with realizing rubber could withstand the wear and tear of being a tyre while retaining its resilience, John Boyd Dunlop and Harvey Ducross together worked through the ensuing considerable difficulties. Their employed inventor Charles Kingston Welch and also acquired other rights and patents which allowed them some limited protection of their pneumatic tyre business's position. Pneumatic tyre would become Dunlop rubber and Dunlop tyres. The development of this technology hinged on myriad engineering advances, including the vulcanization of natural rubber by Charles Goodyear in the United States and independently by Thomas Hancock in Britain, and patented by each separately in 1844. Synthetic rubbers were invented in the laboratories of Bayer in the 1920s. In 1946, Michelin developed the radial tyre method of construction. Michelin had bought the bankrupt Citroën automobile company in 1934, so it was able to fit this new technology immediately. Because of its superiority in handling and fuel economy, use of this technology quickly spread throughout Europe and Asia. In the U.S., the outdated bias-ply tyre construction persisted, with market share of 87% as late as 1967. Delay was caused by tyre and automobile manufacturers in America concerned about transition costs. Quote, in 1968, Consumer Reports, an influential American magazine, acknowledged the superiority of radial construction, setting off a rapid decline in Michelin's competitor technology. Even in the U.S., the radial tyre now has a market share of 100%. Today, over 1 billion tyres are produced annually in over 400 tyre factories. See List of tyre companies. Wheel support. There are two aspects to how pneumatic tyres support the rim of the wheel on which they are mounted. First, tension in the cords pull on the bead uniformly around the wheel, except where it is reduced above the contact patch. Second, the bead transfers that net force to the rim. Air pressure, via the ply cords, exerts tensile force on the entire bead surrounding the wheel rim on which the tyre is mounted, pulling outward in a 360-degree pattern. Thus the bead must have high tensile strength. With no force applied to the outer tread, the bead is pulled equally in all directions. Thus no additional net force is applied to the tyre bead and wheel rim. However, when the tread is pushed inward on one side, this releases some pressure on the corresponding sidewall ply pulling on the bead. Yet the sidewall ply on the other side continues to pull the bead in the opposite direction. Thus the still fully tensioned sidewall ply pulls the tyre bead and wheel rim in the direction opposite to the tread displacement and matching the total force applied to push the tread inward. This sidewall ply to bead tension support was a big reason for older cross-ply cord tyre construction using the materials available in the early 19th century. The cross-ply cord arrangement orients the cords to more directly support the bead and amp wheel rim. However, with improved combinations of cord, bead, rim materials and manufacturing techniques, combined with ongoing focus and research on tire efficiency and durability, it became both feasible and desirable to manufacture radial ply-cord tires, which, for many applications, outperform and more than outlast similar cross-ply cord tire designs by facilitating a flatter contact pattern with more evenly distributed pressure on the momentarily stationary area of contact between tread and amp ground, and lower operating costs over time, due to reduced tire temperature, decreased rolling resistance, lower puncture rates, greater longevity, etc. Manufacturing. Pneumatic tires are manufactured in about 450 tire factories around the world. Over 1 billion tires are manufactured annually, making the tire industry a major consumer of natural rubber. It is estimated that by 2015, 1.72 billion tires are expected to be sold globally. Tire production starts with bulk raw materials such as rubber, carbon black, and chemicals, and produces numerous specialized components that are assembled and cured. Many kinds of rubber are used, the most common being styrene-butadiene copolymer. The article Tire Manufacturing describes the components assembled to make a tire, the various materials used, the manufacturing processes and machinery, and the overall business model. In 2004, $80 billion of tires were sold worldwide. In 2010 it was $140 billion. The top 5 tire manufacturing companies by revenue are Bridgestone, Michelin, Goodyear, Continental, and Pirelli. Materials. The materials of modern pneumatic tires can be divided into 2 groups: the cords that make up the ply and the elastomer which encases them. Cords. The cords which form the ply and bead and provide the tensile strength necessary to contain the inflation pressure can be composed of steel, natural fibers such as cotton or silk, or synthetic fibers such as nylon or Kevlar. Elastomer. The elastomer, which forms the tread and encases the cords to protect them from abrasion and hold them in place, is a key component of pneumatic tire design. It can be composed of various composites of rubber material, the most common being styrene-butadiene copolymer, with other chemical compounds such as silica and carbon black. Rolling resistance. Optimizing rolling resistance in the elastomer material is a key challenge for reducing fuel consumption in the transportation sector. It is estimated that passenger vehicles consume approximately 5 to 15% of its fuel to overcome rolling resistance, while the estimate is understood to be higher for heavy trucks. However, there is a trade-off between rolling resistance and wet traction and grip. While low rolling resistance can be achieved by reducing the viscoelastic properties of the rubber compound, it comes at the cost of wet traction and grip, which requires hysteresis and energy dissipation. A low tangent value at 60 degrees Celsius is used as an indicator of low rolling resistance, while a high tangent value at 0 degrees Celsius is used as an indicator of high wet traction. Designing an elastomer material that can achieve both high wet traction and low rolling resistance is key in achieving safety and fuel efficiency in the transportation sector. The most common elastomer material used today is a styrene-butadiene copolymer. It combines butadiene, which is a highly rubbery polymer that has low hysteresis and thus offers good rolling resistance, with styrene, which is a highly glass polymer that has high hysteresis and thus offers good wet grip properties in addition to wear resistance. Therefore, the ratio of the 2 polymers in the styrene-butadiene copolymer is considered key in determining the glass transition temperature of the material, which is correlated to its grip and resistance properties. Materials science research efforts are underway to improve such properties of elastomers. For instance, this involves modifying the microstructure of the copolymer to control the addition of vinyl butadiene units, as well as the macrostructure of the polymer. Current investigation also involves looking at the functionalization of the elastomer through the addition of filler materials such as silica and carbon black, as well as testing other nanofillers such as nanocellulose crystals, carbon nanotubes, and graphene. Trialkoxymocaptoalkyl silanes are a particularly interesting class of silane bonding agents because of the advantages they afford in reducing both rolling resistance and the emission of volatile substances. Components. A tire carcass is composed of several parts: the tread, bead, side wall, shoulder, and ply. Tread. The tread is the part of the tire that comes in contact with the road surface. The portion that is in contact with the road at a given instant in time is the contact patch. The tread is a thick rubber, or rubber composite compound formulated to provide an appropriate level of traction that does not wear away too quickly. The tread pattern is characterized by the geometrical shape of the grooves, lugs, voids and sipes. Grooves run circumferentially around the tire and are needed to channel away water. Lugs are the portion of the tread design that contacts the road surface. Voids are spaces between lugs that allow the lugs to flex and evacuate water. Tread patterns feature non-symmetrical lug sizes circumferentially to minimize noise levels at discrete frequencies. Sipes are valleys cut across the tire, usually perpendicular to the grooves, which allow the water from the grooves to escape to the sides in an effort to prevent hydroplaning. Treads are often designed to meet specific product marketing positions. High-performance tires have small void ratios to provide more rubber in contact with the road for higher traction, but may be compounded with softer rubber that provides better traction, but wears quickly. Mud and snow tires are designed with higher void ratios to channel away rain and mud, while providing better gripping performance. Tread lug. Tread lugs provide the contact surface necessary to provide traction. As the tread lug enters the road contact area, or footprint, it is compressed. As it rotates through the footprint, it is deformed circumferentially. As it exits the footprint, it recovers to its original shape. During the deformation and recovery cycle, the tire exerts variable forces into the vehicle. These forces are described as force variation. Tread void. Tread voids provide space for the lug to flex and deform as it enters and exits the footprint. Voids also provide channels for rainwater, mud, and snow to be channeled away from the footprint. The void ratio is the void area of the tire divided by the entire tread area. Low void areas have high contact area and therefore higher traction on clean, dry pavement. Rain groove. The rained groove is a design element of the tread pattern specifically arranged to channel water away from the footprint. Rain grooves are circumferential in most truck tires. Many high-performance passenger tires feature rain grooves that are angled from the center toward the sides of the tire. Some tire manufacturers claim that the tread pattern is designed to actively pump water out from under the tire by the action of the tread flexing. This results in a smoother ride in different types of weather. Sipe. Tread lugs often feature small narrow voids, or sipes, that improve the flexibility of the lug to deform as it traverses the footprint area. This reduces shear stress in the lug and reduces heat buildup. Testing of identical siped and unsiped tires showed measurable improvements in snow traction and ice braking performance. However, diminishing and extending braking distances on wet and dry pavement by a few feet on siped tires. Off-road tire enthusiasts have been siping tires for years for greater traction, as many manufacturers now offer already siped off-road tires. Wear bars are raised feet breech is located at the bottom of the tread grooves that indicate the tire has reached its wear limit. When the tread lugs are worn to the point that the wear bars connect across the lugs, the tires are fully worn and should be taken out of service. Most wear bars indicate a remaining tread depth of 1.6 mm and are deemed worn out at that point. Bead. The bead is the part of the tire that contacts the rim on the wheel. The bead is typically reinforced with steel wire and compounded of high-strength, low-flexibility rubber. The bead seats tightly against the two rims on the wheel to ensure that a tubeless tire holds air without leakage. The bead fit is tight to ensure the tire does not shift circumferentially as the wheel rotates. The width of the rim in relationship to the tire is a factor in the handling characteristics of an automobile, because the rim supports the tire's profile. Sidewall. The sidewall is that part of the tire that bridges between the tread and bead. The sidewall is largely rubber but reinforced with fabrica steel cords that provide for tensile strength and flexibility. The sidewall contains air pressure and transmits the torque applied by the drive axle to the tread to create traction but supports little of the weight of the vehicle, as is clear from the total collapse of the tire when punctured. Sidewalls are molded with manufacturer-specific detail, government-mandated warning labels, and other consumer information, and sometimes decorative ornamentation, like white walls. Shoulder. The shoulder is that part of the tire at the edge of the tread as it makes transition to the sidewall. Ply. Plies are layers of relatively inextensible cords embedded in the rubber to hold its shape by preventing the rubber from stretching in response to the internal pressure. The orientations of the plies play a large role in the performance of the tire and is one of the main ways that tires are categorized. Associated components. Several additional components may be required in addition to just the tire to form a functional wheel. Wheel tires are mounted onto wheels that most often have integral rims on their outer edges to hold the tire. Automotive wheels are typically made from pressed and welded steel, or a composite of lightweight metal alloys, such as aluminum or magnesium. These alloy wheels may be either cast or forged. The mounted tire and wheel assembly is then bolted to the vehicle's hub. A decorative hubcap and trim ring may be placed over the wheel rim. The beads of the tire are held on the rim, or the outer edge, of a wheel. These outer edges are shaped to obtain a proper shape on each side, having a radially cylindrical inclined inner wall on which the tire can be mounted. The wheel's rim must be of the proper design and type to hold the bead of the appropriately sized tire. Tires are mounted on the wheel by forcing its beads into the channel formed by the wheel's inner and outer rims. In a tube. Most bicycle tires, many motorcycle tires, and many tires for large vehicles such as buses, heavy trucks, and tractors are designed for use with inner tubes. Inner tubes are torus-shaped balloons made from an impermeable material, such as soft, elastic synthetic rubber, to prevent air leakage. The inner tubes are inserted into the tire and inflated to retain air pressure. Large inner tubes, which are large inflatable toruses, can be reused for other purposes, such as swimming and rafting, tubing, sledding, and skitching. Purpose-built inflatable toruses are also manufactured for these uses, offering choice of colors, fabric covering, handles, decks, and other accessories, and eliminating the protruding valve stem. The valve stem. The valve stem is a tube made of metal or rubber, through which the tire is inflated, with a check valve, typically a Schrader valve on automobiles and most bicycle tires, or a Presta valve on high-performance bicycles. Valve stems usually protrude through the wheel for easy access. They mount directly to the rim, in the case of tubeless tires, or are an integral part of the inner tube. The rubber in valve stems eventually degrades, and, in the case of tubeless tires, replacement of the valve stem at regular intervals with tire replacement reduces the chance of failure. Some may notice that the valve stem is all metal with a nut retaining it. Most modern passenger vehicles are now required to have a tire pressure monitoring system, which usually consists of a valve stem attached to an electronic module. The module is hidden inside and is only visible when the tire has been removed from the wheel. Construction types. Radial tire technology is now the standard design for essentially all automotive tires, but other methods have been used. Bias tire construction utilizes body ply cords that extend diagonally from bead to bead, usually at angles in the range of 30 to 40 degrees, with successive plies laid at opposing angles forming a crisscross pattern to which the tread is applied. The design allows the entire tire body to flex easily, providing the main advantage of this construction of smooth ride on rough surfaces. This cushioning characteristic also causes the major disadvantages of a bias tire: increased rolling resistance and less control and traction at higher speeds. This outdated technology is still made in limited quantities to supply collector vehicles. It is possible to fit older cars with modern tires, if historical authenticity is not paramount. Belted bias. A belted bias tire starts with two or more bias plies to which stabilizer belts are bonded directly beneath the tread. This construction provides smoother ride that is similar to the bias tire, while lessening rolling resistance because the belts increase tread stiffness. The design was introduced by Armstrong, while Goodyear made it popular with the Polyglass trademark tire featuring a polyester carcass with belts of fiberglass. The belted tire starts two main plies of polyester, rayon, or nylon annealed as in conventional tires, and then placed on top are circumferential belts at different angles that improve performance compared to non-belted bias tires. The belts may be fiberglass or steel. This technology was a temporary, not invented here stopgap, introduced by U.S. manufacturers to forestall the radial tire. Radial tire construction utilizes body ply cords extending from the beads and across the tread so that the cords are laid at approximately right angles to the center line of the tread, and parallel to each other, as well as stabilizer belts directly beneath the tread. The belts may be cord or steel. The advantages of this construction include longer tread life, better steering control, fewer blowouts, improved fuel economy, and lower rolling resistance. Disadvantages of the radial tire are harder ride at low speeds on rough roads and in the context of off-roading, decreased self-cleaning ability and lower gripability at low speeds. Following the 1968 Consumer Reports announcement of the superiority of the radial design, radials began an inexorable climb in market share, reaching 100% of the North American market in the 1980s. Solid. Many tires used in industrial and commercial applications are non-pneumatic, and are manufactured from solid rubber and plastic compounds via molding operations. Solid tires include those used for lawnmowers, skateboards, golf carts, scooters, and many types of light industrial vehicles, carts, and trailers. One of the most common applications for solid tires is for material handling equipment. Such tires are installed by means of a hydraulic tire press. Metal semi-pneumatic. Semi-pneumatic tires have a hollow center, but they are not pressurized. They are lightweight, low-cost, puncture-proof, and provide cushioning. These tires often come as a complete assembly with the wheel and even integral ball bearings. They are used on lawnmowers, wheelchairs, and wheelbarrows. They can also be rugged, typically used in industrial applications, and are designed to not pull off the rim under use. Tires that are hollow but are not pressurized have also been designed for automotive use, such as the TheOminousDonut wheel, which is an experimental tire design being developed at Michelin. The outer casing is rubber as in ordinary radial tires, but the interior has special compressible polyurethane springs to contribute to a comfortable ride. Besides the impossibility of going flat, the tires are intended to combine the comfort offered by high-profile tires with the resistance to cornering forces offered by low-profile tires. They have not yet been delivered for broad market use.